last time I talked to you guys, we ended with this sort of discussion of we're talking about binding here, right? We're talking about a protein binding to DNA, like here to here, okay? And how do we measure these things and what do we use? And we talked about the fact that the dissociation constant is what people use to talk about binding, and that's because the dissociation constant, even though it's in the opposite direction that we really want to go in, gives us a concentration unit that tells us the concentration at which these interactions, the equilibrium between these two is significant. So we use the KD, and technically the KD is the concentration at which 50% of your DNA or your protein, whatever is limiting, is in the complex here. Okay? And there are all sorts of things about measuring the KD that we will talk about in a second. But it's important that to interpret this correctly, for the KD to be meaningful, you have to do the experiment right. It's not just simply a matter of throwing things together and getting a number. The number can be meaningless. But again, at the KD, that's where you're 50% bound, which means, tenfold below the KD, you're pretty much not bound, and tenfold above KD, you're fully bound. So pretty much 2 orders of magnitude with KD in the middle is the concentration range over which you should be interested in. So that is the use of the KD for sure. Otherwise, we can calculate free energies from it just like you do normally, but pay attention to signs. If I ask you for the delta G of binding, that should be a favorable number with a negative delta G. Okay. So if you use KDs, that's for dissociation, and so you'll have to make the sign adjustment yourself. Okay? It's not going to come out automatically. You need to think about it. Okay, so affinity is something that we're fairly comfortable with. How strong are the interactions? Specificity is something that you may or may not have talked about, but in this case we're talking about really, if you talk about specificity, you have to be comparing 2 different dissociation constants. And, that sounds straightforward, but it's not really, and we'll get to that in a second. But basically what you're asking is, the protein is given 2 choices, which one does it prefer and by how much? And the ratio of the dissociation constants will give you a specificity. But in DNA protein binding literature, there's all sorts of shenanigans, okay, and just difficulties with doing this type of experiment. What do you choose as your comparison sequence is really important. Okay, so this is kind of how it maps as far as free energy goes. So again, affinity is the absolute KD. However, these numbers that you measure are totally dependent on what conditions you use. In particular, when you're talking about protein and DNA interactions, ionic strength is incredibly important. You can get whatever KD you want by changing ionic strength. And really, that's just simply due to the fact that a substantial amount of protein-DNA interaction, but not all of it, okay, a substantial amount of it is ionic interactions, Coulombic interactions. And essentially, salt can substitute for the protein in that case and can heat it off. And so let's talk about how salt works, because I think there's a lot of confusion with regards to this. That's why I have this little diagram. So when the protein and the DNA are bound, anything that's ionically interacted with is in a hydrogen bond distance. Okay, there is some bulk charge, but basically the protein is as close as it's going to get. It's stuck to the surface of the DNA. So salt doesn't do anything to that. It doesn't interact with that form to change affinity. The way that it changes affinity is by changing the stability, or the free energy of the unbound forms. These are the ones that have unsatisfied charges on them that need to be neutralized, and that's what salt does. So salt does not pry apart this complex. It doesn't do anything to it. Okay? What it does is it makes these guys more favorable, lowers their free energy, again, bringing them closer together. This would be the equivalent to adding denaturant, okay, in a protein folding system. Same thing. Makes the unfolded form in protein denaturing system more stable relative to the folded form. In this case, it reduces the free energy due to unsatisfied ionic interactions in both the protein and the DNA. And as it turns out, we'll find out it really is the protein that's important. The DNA is actually insensitive to salt, and I'll get to this in a little bit, but it's because the salt concentration right around the DNA actually is pretty invariant with regards to external salt concentration, which is not intuitive at all. Okay, so affinity, again, anytime you read a number, if you're going to compare 2 affinities of 2 proteins, they'd have to be done under identical conditions. And even then, it's not clear that that's really a good comparison. So you have to be careful. And in vivo, we don't know at all what's going on, to be perfectly honest with you. Ionically, we have estimates, we have this physiological salt business, but really intracellular salt concentrations are still a topic of great argument. Why? Because there's lots of molecular crowding in there. Okay, specificity gets even worse. The question is, we're talking about specificity, and typically the question in DNA binding proteins is, how specific is my protein for its sequence over all others? Okay? And that's a hard question to really answer, because you have to have a non-specific DNA for comparison. You may ask, why does a protein that binds DNA in one sequence bind to other sequences? And that's simply because DNA, for the most part, at low resolution looks the same. It's a big spiral charge of negatives. So people do all sorts of things to do comparisons. They'll use a defined sequence often. There was an oligonucleotide that's the same size as the target they used for the specific experiment, but they maybe scramble the composition, or scramble the order of the bases, but maintain the composition. And that's fine, but it's one sequence. Okay, it's one sequence. And when you scramble stuff, you still have a 25% chance of retaining at least one nucleotide at each position. Sonic-headed chromosomes, in other words, taking basically a complicated mix of DNA, is also something that has been used. Okay, why sonication? Because remember, sonication delivers small, consistent sized pieces. It's cheap and easy to do, so that's why people do it. But it also suffers from the fact that really chromosomal DNA, although it's quite varied compared to your single sequence, is not random at all. Okay, there's large amounts of repetitive DNA in sonic-headed chromosomes, and those could conceivably have your site embedded in them, unless you know about it. And there are many, many, many repeated structures. As you guys know, 90% of most chromosomes is, or at least human chromosomes, is repeated DNA. So that's not really a good sequence necessarily either. The best thing you can do, in my opinion, is that you can take a piece of DNA that's the same length as your target, but has a randomized sequence in it. And what I mean by that is that, remember we talked about when you make these oligonucleotides, you can allow more than one base to couple at each position. Well, you just do that for all the positions that you're interested in testing for binding. You allow all four bases at those positions, and in the end you end up with a very complex mixture, but at least it's homogeneous in size, okay, and sequence length. And that's important if you're going to do that type of experiment. That turns out to be the best way to do it. Okay. So the other question really is, what does it mean to be specific and non-specific in the context of DNA binding proteins? So I'm going to give you two extremes. One is that a completely specific DNA binding protein binds only one DNA sequence and nothing else. And of course, even that's squishy. What does it mean not to bind something? Okay, does it mean the K is 0, 1, whatever? Okay, so that alone is a problem. And then non-specific DNA binding proteins would be something that bind all sequences equally well. We think of nucleosomes as being non-specific. It turns out they actually aren't. Okay, and there are many DNA binding proteins that bind to lots and lots of sequences that aren't related to each other, but they're still not completely non-specific. And so what I'm going to tell you is that neither of these, okay, are really a realistic viewpoint. Most DNA proteins are in a continuum between being specific for a sequence and being non-specific for it. Why is this? And as I said, one reason that you don't have completely specific DNA binding proteins is that almost all DNA binding proteins recognize some constant feature of the DNA, like the phosphodiester backbone. And that really doesn't change a lot between sequences, although we will show how proteins can actually read those differences later on. And so some elements of recognition are just simply going to be shared, and you can't get away from that. The question is, how many orders of magnitude are there different between any other sequence and your sequence? The other thing is that the reason that most proteins aren't non-specific, okay, meaning that they don't care about the sequence, is that most DNA binding proteins do change DNA structure when they bind. They change either helicity or they bend it, as we'll learn about. And there's a cost for this deformation, and that cost is going to be sequence dependent. For example, I'll mention this again in nucleosomes. We already know that nucleosomes don't like binding poly A and poly T. Why? Because it's stiff. Okay, and where they love to bind poly A T, because that's flexible. It's not because there are any sequence determinants of binding there. There's no sequence direct contacts that would say they exclude poly A or like to bind poly A T. It's just simply because it can bind more easily because it has to deform the DNA when it binds. There's an example of, simple example of specificity by a nucleosome. Nucleosomes also will bind to sequences that actually have certain residues placed in the right position, and we'll get to that as well. So I guess what I'm trying to say is that for non-specificity, you have the problem of DNA structure changing and how there are energetics built into that based on base stacking energies. In the case of specificity, DNA is pretty regularly shaped, and most proteins will have overlapping things that they recognize between DNA binding proteins. And of course, evolution is not going to just simply take a sequence and make it really, really specific for something. That would be kind of like a big evolutionary hole to fall into. Okay, so let's talk about some technology here. And really, there have been lots of ways to measure DNA binding, but a few of them have really lasted. I'm really going to talk much about two, which is the electrophoretic mobility shift assay, or EMSA, or band shift, for those of you who may have heard all that. It's a gel-based assay system. And then I'll talk a little bit about fluorescence polarization and anisotropy, where we'll talk about kind of some physics there. And there are a few others. The others that we won't talk about are surface plasma and resonance, ultracentrifugation, which is really not so great. Or direct observation, say, using AFM. People have actually measured apparent KDs with that. You can do it counting. You just simply lay down molecules and count how many proteins are bound and figure out you're bound or free from that. Okay, let's talk about EMSA, though. That is the most common way that you will read about DNA binding proteins binding to DNA. Okay, in an EMSA, you basically take a small amount of labeled DNA. Okay, your DNA is limiting in these reactions, and you're titrating in different amounts of protein. And in order for this to work, you have to have a very small amount of labeled DNA and a lot of protein. And we'll get to that why that is in a second. But if you have similar amounts of it, this method doesn't work unless you do a quadratic decomposition, which is almost never accurate enough. Okay, so what you do is you make mixtures of protein and DNA with different ratios or different concentrations. You then take those mixtures and electrophoresis them onto a gel at very high speed. In other words, you turn up the voltage, but you cool the thing. Cooling is to really suppress dissociation in the gel. And high speed is for the same reason. You don't want to wait around for these things to dissociate. In this case, the ionic strength you optimize based on really what kind of experimental result you want. And again, reminding you that ionic strengths are really, really an important component of determining what your absolute KD is going to be. Now, this is the squishy part. Some proteins, because there's such a small amount of labeled DNA around, aren't soluble in the absence of DNA at all. And so people add this unlabeled carrier DNA, which is one of those things that we talked about before, like poly-DIC, which I didn't mention, which is basically a DNA analog, sonicated chromosomes, and so forth. And what this stuff does is it really gives a place for the protein to go when it doesn't find its good sequence. But of course, then you're not really looking at the equilibrium between free and bound here. You're looking at the equilibrium between carrier and specific sequence, which is not the same. That's a real problem. People ignore it. What can I say? It's junk. So again, this is where it comes back to be careful of how you define your KDs. And then what you do is you run it out in a gel, and essentially where the DNA is not bound, it will run at a kind of fast mobility, and then where the protein is bound to the DNA, it will be very slow because if you have a large mass that's attached to the DNA, there's also a sense of charge neutralization. And these are under native conditions. SDS obviously won't work because of the nature of the protein and it won't bind. So these are native gels. And simply because the bound and free bands are well separated, you can plot all sorts of things. So let's talk about that. Now, you guys who've been in 123 know about some of these plots I'm going to tell you about. This is a Scatcherd plot. In Scatcherd plots, you basically plot the bound over free ratio, which you can determine by just simply measuring the amounts of radioactivity or signal in each band and then taking their ratio, versus the bound concentration. Now, this is important because this is actually very hard to measure directly, a real concentration. It's one thing to measure what fraction of your stuff is bound, but to put this in real concentration terms is basically nearly impossible. The thing nice about this is the slope is 1 over KD, and the intersect is the concentration of sites that you have, and if you know how much total DNA you have, then you can tell how many sites per molecule. That's all great, but it's really not practical because of this problem. So, and that's also because DNA itself is hard to quantitate. To know the amount of bound form concentration-wise you have to know how much DNA you have. More likely, you'll see something like this, which is a binding isotherm or hyperbolic binding plot. Looks like an enzyme kinetics plot because essentially that's similar to that. In this case, you look at the fraction bound, which again is pretty easy to figure out because it's the amount of DNA that's in your bound band over the sum of the two bands. That's easy to calculate. And then the amount of protein you add, well, if you know your protein concentration, you should be able to figure this out. And then you plot the data like this. And then wherever this guy at a half bound crosses the concentration line, you drop it down. Dissociation constant is that concentration. Okay? Now this is true, only if, okay, and this is really important, only if the amount of protein that you add is far in excess of the amount of DNA you add. Why is this? Because this is the amount of free protein for this to really work. I say protein added, but that's not actually how the formulation goes. It actually is, when you work out the math, this is the free protein concentration. And if a substantial fraction of your added protein is in the bound form, then that number will be in error. Okay? And you will get a sigmoidal shape rather than a hyperbolic shape. But it's not because there's anything fancy going on. It's just simply because you have too much DNA around. And so luckily with radioactivity, you can get down into the femtomolar ranges of concentrations with DNA, and most of the binding constants are close to that. And you're typically titrating in picomolar to micromolar protein. So you're good. And so the rule of thumb here, which I don't have written down, but I'm going to tell you, is that your your DNA concentration needs to be about 1/10 of your expected KD for this to work. Okay, no errors. So if you expect a KD of 1 nanomolar, that means you have to be at 100 picomolar DNA for this to work. Okay? All right. So, sigmoidicity, okay, is something that you will see. And when you see this and you've done the experiment right, let me back up. The way to determine whether you have the right protein concentration or DNA concentration or not is to take the DNA concentration that you're using and cut it in half. If you do that and there's no change in the apparent KD, you're good. That means that the number you're getting does not depend on the amount of DNA target you have. On the other hand, if it changes, then you have to keep reducing the amount of DNA until that stops happening. Okay? Okay. All right. So sigmoidicity is something you'll see in your plots, and this means cooperativity in an enzyme situation. It also means cooperativity when proteins bind DNA. But this is actually rather typical because many proteins bind as multimers, but the multimers aren't assembled until they're on the DNA. And so what happens is the first molecule binds, and then it becomes easier to bind the second molecule, positive cooperativity. Okay? That's sigmoidicity. So if you have a situation, okay, where you're sure about your DNA concentrations and so forth, and you have sigmoidicity, it can mean that multiple proteins are binding and probably interacting with each other. Again, that's positive cooperativity. And the N value, for those of you who care, Hill coefficient and all that, can indicate the maximum number of proteins bound to the DNA, but it doesn't have to do that. It can be less than that. Now, the other reason you have sigmoidicity is mundane but annoying things, like your protein sticks to the side of your tube that you're working in, okay? Which means that the protein that you're actually adding, the free amount is less than you think you're adding. That will also give rise to sigmoidicity. And so you have to be careful that that's not happening, especially if you're working at very, very low protein concentrations. So how big are KDs for protein-DNA interaction? They span the range from really sub-picomolar, which is pretty tight, to micromolar. Pretty much beyond that, they're not useful. So that's 6 orders of magnitude. That's a lot of range. So I can't tell you how it's going to be the case, but typically speaking, for a transcription factor, there's tens to 100 of nanomolar range, which when you calculate the concentration in the cells, about 100 for copies inside of a bacterial cell. Between 10 and 100 copies in a bacterial cell, and in a larger cell like a human, it might be a couple of thousand copies. Okay. All right, so what's going on in an EMSA? This is a picture that's meant to represent the wells of an electrophoretic gel, slab gel. Hopefully you've seen those. This is a well. This is the acrylamide. These are typically acrylamide gels. And this is the well. So, this is where you put your protein-DNA mixture. And, this is how the experiment starts. So if I have my protein concentration at the KD, it means my unbound DNA and my bound DNA are the same. This plus thing is meant to be a protein. And I give it a plus charge because many DNA-binding proteins have a positive charge, but they don't have to have this work. Okay? Now, so at equilibrium inside the gel, inside the well here, before you apply voltage, you have something like this. 50% of these guys are bound. Now, as soon as you apply voltage, now you're not at equilibrium anymore. The unbound proteins are going to probably go that way, or they'll just move more slowly. The bound DNAs and the protein-DNA complexes will probably enter the gel at a comparable rate, but as soon as they're inside the gel, things will be different. Okay? Inside the gel, you may have some dissociation during entry. This is a problem, and I'll show you what the consequences of that. But once they enter the gel, the dissociation is heavily suppressed because inside the gel, it's really like kind of wandering your way through a very dense underbrush. Okay, that's what it's like for the DNA. It's not just kind of ramming straight through a viscous fluid. It's rather it's trying to crawl its way through, as I said, a dense undergrowth or netting. And what that does is if the protein dissociates, it doesn't really have any place to go. It's got restricted diffusion, and it can easily efficiently rebind. And so that's definitely what happens in a lot of cases. In other cases, the factory off rate is quite slow because the binding is tight. So if you kind of do the calculation for diffusion on and so forth, a nanomolar KD gives you, half-lives of hours to days. Okay, so these guys can be quite stable for quite some time. And it says that once they're in the gel, then pretty much dissociation is suppressed unless it's a very fast off rate. So then now if we're going through the gel, what happens is obviously the item with the lowest frictional coefficient and the highest negative charge is going to move faster. And for the most part, as I said, DNA-binding proteins tend to be basic or neutral or slightly negative, but not anywhere close to the negative density of DNA. and they have a large mass, so the mass to charge ratio here is going to be more favorable for these than it is for these as far as moving along. Okay? As I mentioned, if there's dissociation, there's often efficient rebinding, but you can lose some of your molecules here, which will give rise to a little bit of smearing in your gel. So to get this all to work, you have to kind of tune your cross-linker ratio and your temperature, because temperature obviously suppresses dissociation. Everything goes slower at low temperatures, and also your voltage, because the amount of voltage you apply definitely can heat up your gel. That wouldn't be very good, but you want to apply as high voltage as you possibly can without making the gel hot. All right. So there are some critical factors. So in the best of cases, all right, when you have no protein, you get one mobility, and if you add enough protein, you fully occupy your DNA, and you get a nice shifted band and no unbound band at all. That would be the best situation. You can go from completely not bound to bound. Yes?
Can you explain the lines versus the plus?
Yeah, one's a piece of DNA and the other's a protein. Okay. So this is a protein-DNA complex. Everyone good with that? Okay. So back to this. So this case here, this is like your upper band and this is your lower band. Okay. All right. So again, if you can get everybody to occupy your DNA and it's kinetically stable, you should be able to shift away all of your unbound DNA. That's great. More than likely, you end up with a partial shift. And that's because either before you enter the gel, if the two bands are well defined, all this dissociation occurred before you added it. And what will happen in some cases like this is that no matter how much protein you add, you'll never get rid of this, okay, fully. But it will become kind of a constant amount. In which case, you just call 100%, the maximum value of shift that you can get. All right? This is really a nightmare. And this is typically when things aren't going to work, this is what you see. You see a smear. And this is because you have dissociation going on actively in the gel, and so constantly you're changing the nature of your complex, and it's moving faster and faster, eventually leading right up to here. You cannot do anything with this. People try to do this thing where they maybe cut out a band here and then measure the amount above it. That's just baloney, okay? You can't do it. So this is a failure. And then this is a real failure where you basically get no shift at all. And it does happen. There are DNAs and protein combinations that will not give a band shift, and you can never use band shifts to measure it. Okay, so no shift, and this is going to be really clear, no shift, okay, is not evidence for non-binding. It just means that your experiment can do it. That includes with mutants, because mutants can crazily alter the off rate without changing the equilibrium binding constant very much. Okay, and so just because you make a mutation and you don't see binding, you can't say that it abrogated binding. Okay, that's not possible to say that. All you can say is it didn't lead to a shift. And yes, it probably did something not so great to binding, but you can't say it doesn't bind anymore. All right. Okay. So it's the usual thing. This is nothing new in science. If you can't measure it, it's not. So negative data is never informative. Hopefully you've heard that before, but I'm going to say it again. Negative data is never informative. All right. All right, so what do these things look like in reality? This is a funny sort of thing. I decided to go for a more complicated example than the ones we've been talking about. So right here is basically a protein in circle. These are pieces of DNA. And then there are different fragments of this protein with different sizes. Okay, but the DNA binding, part of this is retained in all cases. So again, what you would see with electrophoresis in this direction, okay, is you'd see an unbound form, and then you'd see different sizes depending on how much protein is bound. So for example, for this one, this is a small protein fragment. It gives a shift, but it's a small shift because there's not a large amount of mass. Likewise, you include more of the protein, even if it has nothing to do with DNA binding, but it's still stuck, then it'll go slower, and then the full-size protein will be the slowest. Then perhaps your protein can multimerize in the DNA. There are definitely examples of that, and so you get these larger and larger shifts. The distance between these is not so informative, but generally speaking, if it follows a roughly log molecular weight relationship, you can ascertain that you're seeing one more molecule, or one more unit, I should say, binding, not say one more molecule. In reality, it might look something like this, okay? So here's an example where there are different fragments being added, and then you're seeing larger and larger shifts. Okay. So that's kind of typical. Another thing you can do, and this particular picture needs some help. So I'm going to try and explain that to you a little bit better. So in this case, really, this is your unbound piece of DNA. This is your bound piece. This has nothing added. This is what your shifted band looks like. Now I see one band, and I say to myself, okay, only one protein is binding. But I can't say that. Okay? Because if one band is bound, how do I know whether there are one or two molecules there? I don't necessarily see an intermediate band at intermediate occupancy because maybe this guy is a tight dimer and it never is ever dissociated. I said some cases you do have two proteins that assemble on DNA. In other cases, they're completely tight dimers. And you're never going to see a single molecule bound. So just seeing a single shifted band does not tell you, okay, that you're getting single molecules. However, this is where the gel is kind of screwed up. You can use different size protein variants to sort this out. If you want to ask how many bands, how many different protein molecules are bound, you can do this by using truncated or expanded size bits of protein, fuse it to something else that doesn't interfere with DNA binding. And so in that case, you have mixtures. Okay, if you take a truncated form, then this guy would bind at a certain, it would go at a certain mobility, which would be certainly faster than this. This would go faster because it's smaller. But then if I have a mixture of these two, I'm going to see this, and this, and that will give me three separate bands. Okay? And one of these isn't observed here, which is why I'm kind of saying this bit. But the point is that you'll have a statistical mixture of 1 to 2 to 1, okay, if you have equal amounts of the homodimers of the full-length form, the truncated form, and an intermediate form. If you see that, then you know, okay, that you have more than one species there. It's simple. Okay? And you can certainly get more complicated with that. Again, you may not see this, again, because of the fact that you don't see it because it's kinetically unstable. Okay? So single bands do not imply monomer binding. Okay? And that's really important. All right. So you can get even more complicated. Imagine something which is a tetramer. Okay? And basically now you have a whole mess of other species possible. So if you're dealing with a dimer, you get 2 to 3 species on your gel, and if you have a tetramer, then you have up to 5. So what I'm going to tell you is that you'll have on the order of n plus 1, okay, shifted species up to that many, if n is the number of molecules in your active unit. Yes?
So just regarding this, the previous slide, how do you know it's not using just the dimer falling off?
You don't. That's what I'm saying. So negative results are never evidence. If you see 4 bands, you can say it's a tetramer or more. Or 5 bands of them. Okay? You can say it's a tetramer or more, but you can't say it's not. It's certainly not a trimer because there are too many bands. Okay? But you can't say there aren't, say, 8 of them. Does that make sense? So really the only true information you get by this sort of experiment is that you have more than one molecule bound. And you can get an idea what the lower limit for that is. That's it. Okay? Okay. Everyone good with that? All right. Oh, yeah, one thing I forgot to mention also, kind of back here, is in this experiment they're adding different proteins also to the same mix. Now, one of the questions you might ask is, how do I know that what I'm seeing shifting is really the protein that I'm interested in? And I want you to kind of keep that one in the back of your mind. Okay, let's go back to where I was. So there's another way to measure binding, okay, which is called fluorescence polarization anisotropy. The great advantage of this method is that it's an in-solution equilibrium binding, and it doesn't require a non-equilibrium situation like a gel. Okay, so if you see if there's binding going on, you should see it using fluorescence polarization. Again, if your substrate is well put together. So how does this work? You have a fluorescently labeled DNA, okay, with a fluorophore right at the end. And it turns out that this fluorophore doesn't kind of float around in solution. It tends to stack right on the end because most of these fluorophores are aromatic. So it's somewhat immobilized. Then you add a protein, okay, and what happens is that you don't change the fluorescence here, but you change how quickly this thing tumbles. And it turns out you can use this fluorophore as a probe of tumbling time. That's what we'll talk about. And then if you add another molecule and it tumbles even more slowly, then that's going to give you yet another signal. So there's 2 things you get from a fluorescence polarization or fluorescence anisotropy. These are really the same thing. There's just different ways of manifesting the same thing. You get 2 pieces of information. You get binding constants, and you also get molecular size information if there's more than one molecule involved. Okay, how does this all work? The way this all works is that fluorescence polarization allows you to measure the tumbling time of a molecule. Okay, how quickly it takes for it to reorient itself in solution. And it turns out the larger something is, the more slowly that is going to happen. So small things tumble very quickly, thermal motion. Large things tumble more slowly. And for a spherical molecule, you can actually calculate exactly how long it will take to tumble. through this thing called the rotational correlation time. And rotational correlation time is a little bit hard to explain non-mathematically, but I'll try. It's just simply if you're starting with a particular orientation, a set of molecules in a particular orientation, it's the time it takes for them to have reached the point at which they are no longer correlated with their original position, meaning that they have now tumbled, they've now changed their axes, and now they're no longer oriented. If you wait an infinite amount of time, then they're all going to be randomly oriented, but certainly you'll reach half of that way before then. And that correlation time is directly related to how fast it takes to tumble. And you can do this formula, which you are not to memorize, but it just seems to show that the correlation time is directly correlated with the molecular weight. It also has to do with viscosity, which is kind of what you'd expect. Okay, don't memorize that equation. All right, so that's what you're ultimately after. You're after that rotational correlation time. The question is, how do you get it? Okay, and this is going to require a bit of explanation, so you're going to have to bear with me. So we have not talked about fluorescence at all. How many people have you read 107A and B yet? Okay, good. So this will probably be a bit of a repeat. I forgot to bring some spare paper. Okay, does somebody have something to say? All right. I forgot to bring some spare paper, but I forgot to have my Jablonski diagram included here. So, let's hang on a sec. How many people have heard the term Jablonski diagram? Oh boy, they didn't do their work in 107B, I see. All right. Okay, sorry, it's going to take me a second to do this. It'd take me less time than to dig out a piece of paper. I have another lecture I can pull this out of. I'm sorry, say that again? No, I'm just going to call up an actual lecture. How about that? It's just not for this class. Okay. All right, so let's talk about fluorescence a little bit, because how many people actually here know how fluorescence works? Okay, let's do this. All right. So you all know that they're quantum states. We talked about this a long time ago. You also know that electronic states are the most separated in energy, but each electronic state, excuse me, hello, there it is. Okay, you also know that each electronic state is split into vibrational and rotational states, I hope. Okay? So when you have an excitation with a light wave, okay, it causes a transition, if it's absorbed, between electronic states. But within those states, there are other things going on. And so typically speaking, an absorption event is just simply because you're promoting the electronic transition of an atom or a molecule. Now, what happens when it's excited, okay, is that a bunch of things can happen. One of the things that it can do is it can relax actually back down by tumbling through these vibrational rotational states. And each time it does that, it gives off a little photon of heat, okay, a little infrared photon. And that's why when you shine light on things, they get hot. So that's for most normal substances. However, if you are a fluorescent thing, then what happens is you lose some of your energy through this tumbling down through the excited states. But then you hit an excited state that is more stable than all the others for reasons that have to do with electronic structure. And then you sit there, and then eventually you drop back down and give off a photon. Okay, and that's the fluorescent photon. And this is happening very quickly on the femtosecond time scale, or femtosecond and nanosecond time scale. This typically is about a nanosecond. So continuous illumination gives you continuous photons out. Okay. And you'll notice that this guy has a longer wavelength than this because it's lost energy. That's called a redshift, and that's very typical of fluorescence spectrum. Okay? Now, you can get by all of that and get to the Jablonski diagram. So here's the Jablonski diagram. Okay? You have different promotions from two different excited states into different ground states. That's why I end up with spectra that have multiple peaks in them. They are different fluorescent states that they decay to, giving off heat through internal conversion. There's also this business, which I'm just going to mention, phosphorescence, where these guys cross over to a very, very stable so-called triplet state. These guys last for days sometimes, okay, minutes to days. And so this is the type of thing you see in a glow-in-the-dark poster where you hold it up to light, charge it up. You're putting everybody into this state, and then it decays down slowly over time. But we're really interested in this. So the real thing that I need to get out of this is the fact that, one, a fluorescent photon comes out differently, okay, than the one that goes in. It has a different wavelength. And there's a certain amount of time delay between the time it's excited to the time it relaxes. And that's called the fluorescence lifetime. Okay, that's the first thing I need you to know. The second thing I need you to know, okay, let me get ahead here, all right, is that this can change the polarization, okay, of molecules coming in. And actually, polarization, again, is something which a lot of you don't know about, so sorry for shifting back through this lecture that I give to one of my other classes. Okay, here we go. All right, you know that lights have phase and wavelength and all that, but you also might not know about polarization. What polarization is that, we think of light as being a vibrating electric field. But that electric field vibrates in a particular plane, right? There's a plane here. In this case, it's up and down, as I'm going through. That's called polarization. But of course, the light that's shining on you is not vibrating in any particular plane. There's a bunch of different photons with different polarizations. A polarizing lens will select out one of those polarizations. That's how it gets rid of glare. Okay, and can be very useful, give you a nice picture. So this is just showing here you have an unpolarized light source. It's producing waves of a bunch of different polarizations. Come on. This is driving me crazy. There we go. All right, and just give you one polarization. So what this means at the atomic level, okay, is interesting. So that's the first thing. The second thing, okay, is that when you shine light on a system, okay, why does it absorb light? Okay, well, absorb light because there's an energy difference. But does every single molecule that encounter a photon of the right energy absorb it? No, we know that's not true, right? Because there are different extinction coefficients and so forth. Okay, so there's a different probability of absorption. But one of the things that contributes to the fact that things aren't absorbed is the fact that the polarization of a particular photon has to be aligned with a certain axis in the molecule it's exciting. And that axis is defined by something that's a little bit hard to understand. I'm going to throw it at you anyway. So in order for a photon to be absorbed, this is called a selection rule. Okay, you have to change the difference between the ground state and the excited state must involve an electron distribution change that changes the direction of the dipole. So notice there's a ground state dipole, which is what we think about, but the excited state also has a dipole, and those have to be in different directions for an absorption event to occur, period. It won't happen any other way. Okay? So that means if I have a picture of a molecule here, and I have a ground state dipole and an excited state dipole, they're pointing in different directions, there's a transition dipole that connects the two. What does this have to do with anything? Well, the way to think about this is the direction in which the electron distribution is changing. And in order for an efficient absorption to occur, the polarization of the incoming wave has to align with that transition dipole. In a sense, it's the way that you have to push the electrons to get them to change the electron distribution the way that you want. So, the orientation of the molecule, okay, is critical, okay, for absorption to occur. Are you guys good with that? So basically, transition dipole comes in. This one is aligned. This one's polarization is aligned with the transition dipole, so you get absorption. This one is not, even though they're the same wavelength. Okay. Okay, so, just like I was saying, this is weirding me out. Okay, just like I was saying, basically here is our absorption dipole. Here's an incoming fluorescent photon. Now, this guy, when it emits, is also going to emit a polarized photon. Okay? How? Because its emission dipole, okay, which is just really related to its transition dipole, they're not the same because they're not decaying from the same state. It comes out with a different polarization, but it comes out polarized. So each molecule will only respond to a photon with a particular polarization, and it will emit a polarization of a photon that depends on how it's positioned. So the question is, how does this molecular position change over time between the absorption event and the emission event? That's the key to understanding how this technique works. Okay. And so it's kind of like this. You use a polarized incoming light beam. And what that means is in your solution of molecules, okay, where they're moving around and they're all in random orientations, you're only going to excite a very small fraction of them, the ones that have their transition dipoles aligned in the appropriate way. That's it. So what you do is you're taking a snapshot of a small subset of molecules, and they're all aligned in the same way. If they didn't move, they were frozen over the time scale of the fluorescence lifetime, then they would emit a completely polarized signal. okay, because they haven't moved, and again, they emit along their dipoles, and if the molecules are in only a certain orientation are chosen, only those are, think of it, you're really kind of like illuminating a crystal. And if they don't move, then what comes out of that's going to be related to their initial orientation. On the other hand, if they completely scramble, if they completely scramble their orientation, then what comes out will have no polarization because these guys have now reoriented themselves. Now all the dipoles aren't correlated with each other. The photons coming out have no polarization. That's the key. So the question is, how much does the system evolve away from being completely rigid over time during the fluorescence lifetime? That's the principle. So this is kind of the setup. I might as well just use this. It's also in my notes. You have a typical, come on. This arrow is driving me crazy. I don't know why I'm having so much trouble with this. Okay, there we go. So you have a light source, you have a monochromator. It doesn't have to be 490 nanometers. This is from the thing I took. And there's a polarizer. Okay, and a polarizer is a certain orientation, which they're calling vertical here. Then you have your sample. Okay, and fluorescence needs to be read efficiently. It can be read other ways. But it needs to be read efficiently by going 90 degrees to the incoming beam, because then you're not getting contamination of the incoming beam. And then here you have two polarizers that are 90 degrees apart from each other, and you're comparing the signal between the two. If you're shining an unpolarized light on this, then the signals from these two should be the same, right? Because you're studying all molecules and you're having all polarizations being represented. On the other hand, kind of an extreme case is if I use a vertical polarizer and basically I have a solid sample where nothing is able to move, then I should get all the signal out in one side and none of it out in the other, right? Does that make sense? Okay. But if the system can evolve, okay, so the molecules can change orientation, then I'm going to get some mixture, okay, of signal here and signal here. And that's what the anisotropy is. So the anisotropy is defined as, again, you don't have to know any of this stuff for exam, okay, I'm just telling you. It's the difference in the vertical and horizontally polarized signals over this little extra term here, which I'm not going to get into, but basically over a normalization term. So it goes from more or less 0 when these guys are the same, there's no anisotropy, to if these guys are both, if this is 1 and this is 0, then basically it goes to 1. So it's 0 to 1. Okay, so what does that do for you? Well, you can also come up with an equation that tells you how this anisotropy relates to two things, the fluorescence lifetime and the tumbling time, because that's what's important. It's the fractional difference, or the fractional ratio of those two. Excuse me. Oh, this is really driving me crazy. All right. So if you look at this equation, the tau in this case is the fluorescence lifetime, how many nanoseconds, which is typically what it is, and this is the tumbling time. So essentially, if the tumbling time is much bigger than the fluorescence lifetime, in other words, it takes a lot longer for the thing to orient itself, then basically you're going to get an anisotropy that's going to be the maximum anisotropy. That's what A0 is. Okay? Because this term is going to go to 0. Because this is so much bigger than that, meaning a very slow tumbling time, a rigid sample. On the other hand, if this is very big compared to that, this number is going to be a lot bigger than 1, and then this thing will go to 0. That means you have no polarization of your outgoing signals. Okay? All right, so now I'm going to skip back to my other lecture. Sorry about that digression, but I also felt like we had time for it. Okay. See, same figure. All right. So what does that mean? It means basically if I can measure anisotropy as a function of protein concentration, I'm going to get different tumbling times to the molecule because different fractions. Oh yeah, one thing I forgot to mention, in a two-component system, the anisotropy you measure will be the weighted average between the two molecules in the system. Okay? So there's no problem with the fact that you have two discrete populations of anisotropies. It works itself out. And so what you see is something like this. You measure anisotropy as a function of the amount of protein you add, and you see signals like this. You can get a binding curve. So each one of these dots represents a different protein concentration. And so this guy is Krebs, which is a very small protein, bound to a fairly short oligonucleotide, okay, which has a pretty fast tumbling time. Now you add Krebs to it, it slows down. And so you get this decrease in tumbling time, an increase in anisotropy. Now you add all three of these guys. Okay, this is really big, Krebs binding protein is really big, and so you get a very nice big anisotropy. And it turns out, if you work out the math, actually although this is binding, giving a more weak anisotropy. This one actually binds tighter than when all three are connected together. That's not untypical. Okay, so that's how you measure. You basically develop an isotherm and you analyze it just like you would gel data. Sorry for that long explanation, but I think it's important to understand the underlying physics for these guys. Am I going to ask you that on an exam? No. Okay? All right, but I will ask you about stuff like this. So those are the two methods that we have for measuring DNA binding. Pretty much all the other ones are either variations or just so much less good that nobody uses them. Okay? The limitation that you have with fluorescence anisotropy and all fluorescence measurements is how good your fluorophore is, how bright it is. Because you have to be able to measure the fluorescence to get fluorescence anisotropy, and most dyes really can't go too much below 5 nanomolar to a nanomolar. So that is going to be the limit to what you can measure. Okay. All right. So there are different ways to recognize protein and DNA. We're going to go through each one of these. One is through charge-charge interactions. And again, most DNA binding proteins, in fact, all of them I know, have a basic DNA binding face. They have a face that has positive charges on it that are going to want to interact with the negative charges of DNA. That's first. So that's just kind of typical Coulombic stuff. Can't calculate it for reasons we've talked about. Okay. Then there are shape-specific interactions. Again, lock and key fit. And this isn't the case of where is this all going on. This is going on in the grooves of the DNA, because this is where you have a complementary surface, not only to the double helix, but also to the bases in the grooves. Okay? But the shape-specific interactions I'm talking about here are the ones that have to do with the double helix. And so you'll have helices stuck in the major groove because they're convex surfaces. They're sticking out. And then there might be a valley in the protein that also accommodates the phosphodiester backbone, which forms a ridge, as you know, along the DNA. Then there are hydrogen bonds and salt links and van der Waals contacts, okay, to the phosphodiester backbone. We're mostly interested in hydrogen bonds and salt links, and really these are the same. The only difference between a hydrogen bond and a salt link at this point is that this envisions a hydrogen bond between a charged side chain and a normal one. But you can also have uncharged side chains making very nice hydrogen bonds. So these are all phosphodiester backbone interactions. We haven't talked about the bases yet. The last thing I want to talk to you about is a little bit of a digression, but it ends up being important. This is called counterion release. And it tells us something about DNA that we wouldn't necessarily guess by looking at it. So counterion condensation is an idea that was put forth by Manning, who's a thermodynamicist. And like all thermodynamicists, if you try and read their papers, they're incomprehensible. So that's how it goes. I think I gave it to you, but you can have fun wading through it if you want. So the way that he envisioned in his original formulations DNA is this being a 20 angstrom wide negatively charged wire. And when he did his calculations for this, what he found is that the prediction is that there would be a high concentration of counterions, cations, around that would be a certain thickness, and after that would fall off very quickly. So that's the first thing, is that there's this sheath of ions around nucleic acids. Okay? In spite of that, no matter how many ions you add to solution, it won't change the depth of this. And it won't ever completely neutralize the DNA. The only thing that determines how much of the DNA charge is neutralized is the valence of the ion that you add. And so he has this formula, which you're not going to memorize either, which basically shows that if I have a monovalent ion, the best I can do is neutralize 75 or 76% of the charge. I can't do better than that. No matter how many molar of salt I add, I can't reduce the charge anymore. If I go to magnesium, then I get up to 88%. But if I add a multivalent ion like a protein, then I can neutralize up to 98%. What this says is that multivalent ions have an extreme binding advantage over monovalent ions, which is how they're able to compete, for binding to DNA. The second thing it says is that you can never completely neutralize this, meaning that it doesn't matter how much salt you add in an external solution, you're not going to change the concentration of the ions. And you can't desalt. Okay? So what does this have to do with DNA binding proteins? It means that DNA binding proteins with multiple charges, as I said, have a binding advantage. And this is basically driven by the entropy of ion release. You're releasing a lot of ions, for a few molecules binding. And we know from our discussion of the hydrophobic effect, which this is not, because there's no delta CP associated with this particular part. But nonetheless, there's still an entropy of ion release to be taken. If I take a DNA solution and I pass it over a gel filtration column or some sort of desalting or I dialyze it, I'm never going to get rid of those ions. They are permanently stuck. I can replace them, but I can't get rid of them. It's too high energy. So you can get rid of the external stuff, but you can't get rid of what's bound to the DNA. It also tells us, I think, pretty clearly that the reason when we add salt to protein-DNA interactions, we disrupt them, is that we're stabilizing the free protein, not the DNA, because the DNA's ion neutralization doesn't change. Another thing that I didn't talk about in detail here, but he also showed that the ions moving along the DNA are pretty much there's no activation barriers, so it's not like they're stuck to particular phosphates. They can just move pretty quickly along the DNA axis. Okay? It also suggests that maybe proteins themselves can also slide along the DNA, but we'll talk about that later. Okay, what's going on with this? All right, so this is DNA structure stuff. Let's talk about what we're really interested in, what I find most interesting, is how a particular sequence of DNA is read. And really, the only place that a DNA protein can directly read the sequence of a DNA is in the grooves of the DNA. Why? Because this is where the bases are actually touching water. The phosphodiesterase backbone covers the sugars, okay, so they can't really be detected. But the edges of the bases, remember, are sticking into the grooves. This is why in the beginning of the class I made such a big deal about what groups are sticking to the major and minor groove, because this is what proteins are seeing. So if you're trying to understand how a protein can recognize DNA, you have to think about what it can see. So let's look at an AT base pair. Why is this AT? Because A is on the left. Come on. Because A is on the left and T is on the right. If it were TA base pair, I'd just reverse them. Okay? And it would be the same. So remember, if I draw them this way, the minor groove's on the bottom, the major groove's on the top. Now, if we look at what information we have to look at here, we've got N7 here. We've got the exocyclic N6 here. We've got O4 here. In the case of thymine, we have a methyl group. That's distinctive. In the minor groove, so we have a acceptor, a donor, an acceptor, and then a bump. Here we have an acceptor, a space, and we have an acceptor, okay, in the minor group. So different information, but still enough to differentiate, because if we go to other base pairs, we can see that this is not the same. Excuse me. So let's compare this to a GC base pair. All purines have an acceptor here. Okay, so in theory, they shouldn't be distinguishable by interactions here. What I'm going to tell you is they are, and it's not clear why. AT base pair has a donor here, but a GC base pair has an acceptor, so that's different. And here there's an acceptor in an AT base pair and a donor. And here there's a bump of a thymine methyl, but with C doesn't have that. So clearly in the major group, these guys look really different, okay, in terms of hydrogen bond patterning and also van der Waals contacts. And if you laugh about the van der Waals contacts, it turns out that, remarkably enough, the major way that T is recognized by DNA binding proteins is through that methyl group. They've evolved to do that. Okay, so it must be a really good way to distinguish them. In the minor group, things are also different. In AT base pair, you have a space, okay, an acceptor, a space, and then you have another acceptor. Whereas in a GC base pair, you have an acceptor, donor, acceptor pattern, and sterically quite different. So I think you can see that these sort of base pairs, and if I flip them, it's kind of the same thing, are easily distinguishable by a protein. Okay, there's nothing here that would suggest that this would be hard. There are also additional mechanisms. And obviously, an AT base pair and a TA base pair are not the same. You're flipping the information. So obviously, molecules have a handedness. They can easily tell the difference between this and this. They're quite different. Okay. Let's look at an example of this. So essentially, when a protein contacts a base in DNA, like what we see going on here, that's called direct readout. And it's just simply a case of where the protein is making direct contacts with the DNA base. And the contacts can either be really direct, in other words, the side chain is essentially making a hydrogen bond or a van der Waals contact with the base, or they can actually be mediated through an intervening water molecule. And it used to be thought that these intervening water molecules were not really very stable, and therefore this wasn't really a specific interaction. But now this is absolutely known to be the case. There's a guy named Paul Sigler who died some years ago who really spent about, the last 6 years of his career convincing people that these were real, and I think it really did. And kind of the way he did that is he was looking at TRP repressor bound to DNA. TRP repressor is a DNA binding transcription factor from bacteria. And what they noticed in the case of TRP repressor, which is quite interesting, is that there were a lot of water bridge contacts. And when he first tried to publish the structure of that in Nature, they rejected it and said, this is a non-specific complex. You're not really seeing real protein DNA binding. And so he ended up getting about 6 or 7 more papers out of this, really showing that that was not true, that it really was a specific complex. And so one of the things they did is they did a crystal structure of a DNA protein complex, and this is just showing the DNA and showing the location of water molecules in that DNA. And these are actually bridged to the protein to make contacts. he showed that many of these water molecule positions were also in the free DNA complex. So they are really topographic features of the DNA, and they bind there in those particular sequences because those are good places for them to bind. And again, this is an example of what he saw in the structures, again, which is now, I think, by mutational analysis, there we go, to be pretty much the case. You see that although there's a direct contact here, there's a number of other water bridge contacts, and these really do end up being specific. So just because it's water bridge doesn't mean it's not real. Okay. Now, single interactions with DNA, even if you add them up, aren't really going to give you the discrimination that we see between proteins recognized in their actual sequence and sequences like it. What I mean by that is that if I have, say, 3 contacts that are worth 1 kcal per mole each, then if one of them is missing, then I have only a 1 kcal difference between them. That's not really a very big discrimination. That's maybe a factor of 6, okay, or something like that. So we see much bigger discriminations in DNA binding proteins. We typically see factors of 10 to 100 by just changing a single base pair in the recognition sequence. So how is that possible? That's possible by the fact that rather than each contact being independent, proteins have evolved to make these contacts interdependent. So here's an example. These are called recognition networks. These are much like the networks of hydrogen bonds inside the middle of a protein. Same idea. So what we have in interdependent protein contacts is each contact is not independent, but it depends on each other. Look at this sequence here. This is from a restriction enzyme called HINK2. Anyone who's done recombinant DNA has probably heard of this guy. Restriction enzymes typically represent palindromic 6 base pair sequences, which means this side and this side are the same. They're just going in opposite directions. And so really what the protein is recognizing is half of the site because restriction enzymes tend to bind as dimers. Okay? And whenever you see this palindromic recognition sort of thing, you should be thinking protein dimer because this has symmetry and so does the protein dimer, which is the same. Okay? All right. So these are the base pairs that are important, and they're underlined here. Underlined here and in this picture. So on one strand, there's a G that's recognized by glutamine residue, and it's got a donor here and acceptor here. But this donor is also fixed to another glutamine residue that's not making base-specific contacts, but instead is bridging hydrogen bonds all the way to this other specificity-determining residue, an asparagine, that's making a acceptor-donor interaction with this adenine across the strand. Okay? And then this is not only making a connection here, it's also making a second connection to the adjacent guanine. So this is called a bidentate interaction because it's recognizing 2 base pairs at once. Okay, and the only way it's going to recognize these base pairs are the 2 purines. And furthermore, what I'm going to tell you is that the disposition of this N7 depends on whether this is an AT base pair. If you make this GC base pair or not, if you make an AT base pair, this isn't where you think it is, and so it can't recognize that. Now, if there's not an interaction here, let's say this G is missing, then this guy is going to wiggle around a bit, which in turn is going to wiggle this around a bit, which in turn is going to weaken this interaction. Likewise, if these 2 bases aren't exactly there, then this is going to wiggle, and it's going to loosen up this interaction. So these 2 interactions are tied together by this intervening residue. If you delete that residue, the thing doesn't bind at all. Okay? It is necessary to orient these dyes to get high specificity. So again, it's a kind of, I wouldn't call it quite all or none, but a near all or none recognition network. Either everything's there or nothing's there. And that gives much higher specificity. Now these guys, the restriction enzymes bind with incredibly, I shouldn't say they bind, they cut with incredibly exquisite specificity, about 1 incorrect cleavage for every 10 to the 6th to 10 to the 8th real cleavages. Turns out that's necessary because remember restriction systems we talked about a while ago. These are enzymes that live inside of bacteria and they go and cleave incoming DNA. And they protect themselves with a methylase enzyme. Now, if they cut frequently where the enzyme doesn't, the methylase enzyme doesn't methylate, then they will kill themselves. And most bacterial genomes are on the order of 1 to 10 megabases. So it actually makes sense that their accuracy is better than that. It means they're unlikely to cut their own DNA. Okay, so that's good. So they've evolved these very high specificities. Interestingly enough, a lot of the specificity actually doesn't have to do with binding so much. Many of them have very poor binding specificities, but instead it has to do with their transition state is very explicitly exquisite for a particular DNA sequence. Okay, so that's direct readout. Indirect readout is really where you're not touching the bases directly, but you're measuring something about the DNA. And a lot of times, this indirect readout doesn't occur by base-specific contacts. In fact, it rarely does. It actually is through backbone contacts. And here's the idea. if you have the DNA, okay, most proteins when they bind DNA do something to the DNA that's different from being perfect B. Okay, typically there's a little bit of unwinding. There's very often a big bend being put in, or sometimes complete unwinding and complete unstacking. We talked about that early on when we were talking about bending a while ago. And these deformations may be required to make a backbone contact. So if you have a protein that's roughly spherical and you're wrapping the protein around it, you have to bend it in order to make the contacts, okay, with the backbone. And it turns out that the ability to deform the DNA in that particular way is sequence specific. We know that. Why? Because stacking energies of different base steps are different. And they also deform in particularly different directions. Okay, so you can imagine how the sequence might influence the ability of a protein to bend in a particular way energetically, and that in turn is read by the protein. It's sequence specific in the sense that the sequence that it recognizes is probably the best sequence for doing that, and anything that's away from that, anything that requires additional energy is going to cost you. So it's kind of like this. I'm showing these guys bound, but that's probably not what's really true. Though there are examples, and I'll tell you one in a second, where you do have binding to both a bent and a straight form. But really, this is probably not occurring until you bend. Now, if you bend a non-specific DNA, you can now make the contacts that you need to make, but you're also paying for bending. So that increases the energy of the system. On the other hand, if the energy for bending a particular sequence is lower, then this is going to be preferred over this because you don't have to pay that extra bending energy. Let me give you an example. We talked about phage lambda repressor. Phage 434 is a lambda-like bacteriophage, and it has a repressor like the lambda repressor I talked about. And it binds to an inverted repeat. So it binds to this inverted repeat, which is roughly 18 base pairs, I think, or 17 base pairs, but it makes no central contacts, no contacts at all with the central 4 bases. And yet, if you make mutations in that central 4 bases, you can change a lot. So the normal native site has a TPA base step. What's significant about TPA base steps? Remind you guys. This is the sort of thing that we're talking about in terms of cumulative knowledge. You got to remember. So what's significant about a TPA base step? It's the most bendable, or TPA and TPG are the most bendable sites. So this guy, when it binds, makes about a 60-degree bend in the DNA. So this gives a certain K of this, and these are K associations, not dissociations. When you put in a very much less bendable GC base pair, you lose basically 60-fold binding. Okay, 60-fold binding difference between these two. There's no direct contacts, and yet that's a pretty big change in specificity. So this is, I think, a nice clear case of indirect readout.
So do indirect readouts have lower specificity than direct readouts?
No, they increase it. Because typically it's a mixture of both. So this is a case where you have a mixture of both. You have clear base-specific contacts that have to be made on either side of the DNA that it binds to. But in order to do that, you have to bend the DNA to get there. And so anything that costs you to do that in excess, okay, is going to differentiate your binding. So again, the two arms that it's binding to are the same in both of these cases. The only thing different is this base step in the middle. And this is much less bendable than that one, and so it costs 60-fold. And it turns out, roughly speaking, it's about the bending energy difference between these. Okay. Is everyone clear about that? So this is important. Indirect readout really is about the costs of deformations outside of it. I mean, I'm talking about bending now because it's the easiest one to figure out. But again, it could be unwinding, it could be unstacking at bases, any of those things. It all comes down to stacking energies. Okay. And in fact, one of the questions, this is kind of an old story, but I might as well tell you about it, is that in the early days when this was noticed, people said, well, because they were using, remember the gels we talked about for measuring bending a long time ago, they were looking at protein-DNA interactions that way. And they said, wow, it looks to us like in these gels that the non-specific complexes are less bent than the specific ones. And it turns out they were wrong, okay? Because if you use AFM to measure this bend angle for proteins bound to DNA, these guys showed quite some time ago that basically, whether it's specifically bound or non-specifically bound, the DNA bends exactly the same amount. And that makes sense. If you're going to make backbone contacts by bending the DNA, you have to bend it the same amount to make those contacts in order to stick. It's just the energetics of those are different. Excuse me. Okay. So here's a story that's slightly different. Okay, so EcoR5 actually binds both these and this. EcoR5 is another restriction enzyme. Okay, and it binds actually non-specific complexes straight, and it binds specific complexes bent. It cuts these, but it doesn't cut those. Okay, so here's the case where it seems like you'd have a low specificity, but EcoR5 has a wonderful specificity just as much as the other ones, and yet it binds both of these about the same affinity, which is picomolar. Okay, so it's very tight binding. So if you put EcoR5 into a cell, it's going to find and bind to a bunch of DNAs. But we'll only cut this one because this is what it takes to put the whole active site into the right configuration so it'll cut and bind magnesium. Puts all the hydrogen bond donors and acceptors in the right places that then orients the magnesium binding site that's necessary for catalysis, and then catalysis can occur. So that's another way that deformations can control activity. Not through binding affinity, but actually through specificity. Okay. All right. So again, you can use EMSAs to look at all of this. And, I've put a lot of things into this slide, which makes you think that I'm not going to ask you details about it, which is true, but I want you to understand this. So, again, using EMSAs, how do you remember there was this business of fragment permutation, where you had a binding fragment and you would distribute throughout a piece of linear DNA. And you would get differences in mobility depending on where that bend was in the larger piece of DNA that you're looking at. And so this is meant to show as you permute the fragment through different positions of the DNA, these are the relative mobilities. Where the DNA fragment is closest to the center of the larger fragment, it's going to be slowest. That's the slowest mobility. And where it's towards the end, it's going to be fastest. However, the depth of these binding plots or binding differences that you get in circuit permutation do not tell you the bend angle. Okay? People thought it couldn't be fast, but it can. And this is the reason. It's because when DNA binding proteins bind to DNA, they distribute differently depending on their specificity. A non-specific DNA binding protein will distribute itself evenly all the way across this. And therefore, there will really be no difference, okay, in mobility. If this guy is binding in all sorts of places along the edge, it doesn't matter, whether it's bound in the middle or not. You're just going to get no change in mobility. On the other hand, the more concentrated it is, the more singular its binding is, the deeper a difference you're going to get. I guess what I'm trying to say is you can have perfectly specific binding going on and it looks like this, okay? But if you see something like this, it definitely means that you have some bending going on and some specificity. But not seeing differences does not necessarily mean that there's no bending going on. Again, negative results aren't useful. The second thing you can use gels for in this, and I'm not going to test you on this at all, because nobody uses this much, is the idea that you can also see looping. Okay, and this would be for proteins that bind more than one DNA sequence that's in a tandem repeat. For example, your old friend lactopressin you guys learned about, you probably didn't learn the fact that it actually has two sequences that it binds to. It binds as a dimer to each one of them, and then it's a tetramer that binds both, and it forms a loop. Okay, and that loop is actually important for regulation. So let's say we were looking at two tandem DNA sites that might be spaced apart by a couple hundred base pairs, like in lactopressin. And so you add enough protein to bind one of these sites. You either get it bound here or here, so you have potentially two different shifted species. Then this guy could also, with a small amount of protein bound, this guy could also form a loop. And this is going to have a different mobility than this one. Loops have definitely different mobilities. If I add a lot of protein, though, what's going to happen is now I can start forming bridge species, which can have yet different mobilities. And then if I add yet more protein, I can't even form bridge species because I basically competed out all the sites with protein. And so that could give some really weird patterns of protein-dependent mobility. So, for example, here's the unshifted DNA. I add B, I get a certain shift. Then I get a loop formed, so just a certain amount of protein, I might see both of these present, okay, at the same time, and that equilibrium is going to depend on the difference in bending energy, bending energy here. Then I add more protein, now all of a sudden I get really big things. Then I add even more protein, and now I go back to getting smaller things, okay? So that would be really weird, right? And that weirdness occurs because you have many different species that could possibly be formed. So interpreting these ends up being quite tricky, okay, or can be. So that's one thing you can find out by doing this. The second thing you can find out is something about what the orientation of these sites needs to be. So in the natural operator, in the natural DNA binding spaces, you expect these to be aligned in somewhat optimal configuration. But now if I flip this 180 degrees with respect to this is phasing. If I add a half a turn of DNA in between these, now I'm going to flip one binding site from one side to the other. Okay, 180 degrees away. That's going to be hard for it to form a loop. It's not going to be able to form a loop at all. So looping will go away. Then if I add yet another 5 base pairs to get 10 base pairs, now I have a full turn difference. This site has come back into phase with this one, and now I get looping. So again, you can use this as a way of inferring whether looping is occurring or not. And you can also get information about what orientation of the sites is necessary. Okay. So I'm going to finish. I'm going to stop here. I'm going to take up later because we need to get to our exam. So what I'm going to do is take a break, and while we're taking the break, I'm going to hand back the exams. All right, I'm going to do it just like I did before. I'm going to set up some chairs here. I'm going to call out certain last names. Come and get those, and then when those are done, then I can put out the next thing. By the way, some of you asked me about previous exams. I have those too, but you'll come up to me for those directly. Okay, A and B. A and B are going to be right here. C and D. F and G. If you guys can come immediately and do this, because I can't put down other papers until people have gone through all of theirs. So please be speedy about this.
So the stuff with the direct and indirect readouts, I don't understand why indirect wouldn't be less specific because it doesn't exactly depend on the sequence.
Okay, so I see what you're saying in a way, but it depends on how specific the definition is. In general, I would say you're right. Okay, but I don't want to say it's always that way. Because there are examples of cases where it looks like a completely indirect, and it's very specific. Like you can do an experiment we'll talk about later. Lego selection. You have one sequence out, and yet when you do this instruction, there's no direct line. So, but that's unusual. You're right.
And you can have direct and indirect at the same time.
Oh, absolutely.
Okay.
Okay, why don't you go through this file? It only take you so. Okay.
Yeah.
Okay.
Yeah.
Okay, M and N we're up to. We went up to. Oh, they're right there. Sorry. Yeah, go for it. Please only take your own though.
I got this.
R. Okay, F. F and T over here. Okay, what number? What are you looking for?
My old exam.
No, I'm sorry. I'm talking to this person.
Oh.
What are you looking for? M. M is down. It's in that pile over there. Oh, wait, sorry. Right here in my hand. Okay.
Oh, yeah. Yeah.
Okay. Okay, V and W. And all the rest, well, it basically does. Okay, X through Z.